Moving from one dimension to the 3D particle in a box, we will see how the symmetry of the three dimensions leads to states of the same energy, or degeneracy. We will start with a mathematical solution to the 3D infinite potential well problem. In each of the three dimensions, we have the same problem as we had with the one-dimensional infinite potential well. Namely, between 0 and A, we have a zero potential, but outside the box, when x is greater than A, the potential is infinite. Or, outside the box, when x is less than 0, the potential is also infinite. We will use similar conditions along the y and z directions, having a box width b and height c, although we will mostly be interested in the square box case when a equals b equals c. To solve for the wave function, we will use the 3D Schrödinger equation, where the Laplacian and the potential will depend on x, y, and z. Using again the method of separation of variables to simplify the problem, we postulate that the wave function is simply the product of an x-dependent wave function, y-dependent wave function, and z-dependent wave function. Substituting this form of the wave function into the Schrödinger equation, we again see that we can separate the x-dependent part of the wave function from the y-dependent part of the wave function and the z-dependent part in the Laplacian part of the wave function. With x, y, and z now separated, this equation is the same as three single-dimension equations, such as that given here for x. This equation is exactly the one-dimensional particle-in-a-box Schrödinger equation that we solved previously. As we found before, the wave function solution are sine waves, where the wave vector must be an integral number of pi over a. And the energy must be h squared over 8m, the quantum number squared divided by a squared. Solving now the similar solutions for y and z, we also get sine waves that then we plug into our equation for the full wave function, giving us a full wave function, the product of sine waves along x, y, and z, where each dimension has its own quantum number, n1, n2, and n3. When we plug this wave function into our Schrödinger equation, we will find that the energy equals the sum of the energy from each x, y, and z wave function, meaning that the energy will be h squared over 8ma squared times the sum of the squares of the quantum numbers, where for convenience we have now assumed a equals b equals c. We often write the sum of the squares of the x, y, and z quantum numbers as an energy quantum number squared, so we can simply write the energy as h squared n squared over 8ma squared. The higher dimension wave functions have similarities to those of the one-dimensional wave functions for particle in a box. The ground state wave function is the smallest wave to fit within the size of the box and has no nodes. In 2 dimensions, with the wave function formula given here, the ground state again is the smallest wave to fit within the size of this 2-dimensional box. Here we use a 3rd dimension to show the height of the wave, and here is a contour plot in 2 dimensions. This 2D ground state wave function is like the fundamental vibration of a membrane on a square drum. The first excited state is the next shorter wavelength wave that will fit inside the box and has one node. In 2 dimensions, this node is a one-dimensional line as depicted in this wave function here. Due to the symmetry of our square box, having the node in the x direction or the y direction gives a wave function of the same energy, and so we have 2 degenerate states, one with n sub x equals to 2 and ny equals 1, and the other with nx equals 1 and ny equals 2. In 3 dimensions, we will see 3 degenerate states of this first excited state. As before, higher energy wave functions have even shorter wavelengths and more nodes. As we saw before, the quantization of the wave functions comes from its confinement to a specific location in space. The new feature we find in the higher dimensions is the degeneracy of some of these excited states. By degeneracy, we mean different states that have the same energy, where the degeneracy originates from the symmetry of the x and y dimensions. Again, we have the principle that more nodes equals more energy, but in higher dimension, our nodes have higher dimension also. In 1D, a node is a 0D point, whereas in 2D, a node is a one-dimensional line. And finally, although quantum mechanics limits the possible states, in higher dimensions, the number of states increases rapidly as energy increases. Degeneracy happens quite frequently in 3 dimensions, as we will see in the 3-dimensional particle in a box, where, remember, the energy is proportional to n squared, where n squared is the sum of the square of the quantum numbers along the x, y, and z directions. We can start by making a table of n squared for successive quantum numbers n1, n2, and n3. For example, when n1, n2, and n3 are 1, then n squared is simply 3. The excited state has n1 equals 2, n2 equals 1, or n3 equals 1, which has the same energy as 1, 2, 1, or 1, 1, 2. And so all of these are the same with n squared equals 4 plus 1 is 6. On the plot on the left, we show the number of states versus energy, or what we really mean is n squared, where our ground state shows up at n squared equals 3 with only one state, and our first excited state shows up at n squared equals 6, where there are 3 states. As we look higher in energy, we see relatively few states which only have one state of a particular energy, and we see many times multiply degenerate states. In fact, we see states with even higher levels of degeneracy as we move higher in energy. As we look higher in energy, we see a continuing trend of the number of states increasing with energy, where we see the form that starts to look like a square root function.